Well, we were just informally talking that we are all happy that this is the last day. I know you all of you work very hard, and you may be a little nervous about today's presentation, but I mean, it's no big deal. I mean, you know each other by now. It's going to be okay. Okay, so the first presentation, Harald Bedi couldn't be with us today, so I believe Dr. Lee is going to show his recording. He record a presentation for us to watch it. So, Diane, are you ready?
Hi again.
Good to see you all. Today I will be presenting to you my 10 weeks effort of building my project called R-Trees, which is an R package written to generate phylogenetic trees for ecologists. So what is R-Trees? R-Trees is an R package written to derive genetic ancestral trees of any given species. The ultimate goal of this package is to remove the barriers of deriving such phylogenies without any prior knowledge of programming from the user. Commonly, there are many similar softwares that generate lines of code, which then the user would run on their local machine in RStudios. Now, the problem occurs when a student or staff with no prior programming runs into syntax errors in between the copying and pasting process. In order to eliminate this hassle altogether, under the guidance of Dr. Dejang Lee, we produced R-Trees, which reduces the user's efforts tremendously. With the help of RShiny and its user-friendly interface, we were able to build and maintain R-Trees' integral functions, as well as preserve its ability to be used by the novice user. So exactly, how did we achieve this? The Shiny application consists of two key components: the server that runs your R code, and a user interface that runs through the user's web browser or local machine. The UI will contain a layout which can place input fields and outputs, such as visualizations. Input fields are things like text boxes, drop-down menus, calendar control, that send their values back to the R server. The R server then updates calculations and those visualizations, which get sent back to the UI to be displayed to the user. It's important to note that the Shiny application always needs a user running R to work. Now it's time for a small demonstration of this. So firstly, we would prompt the user to select one of these taxons as the first parameter, whether the species of interest is a plant, fish, bird, mammal, or other. Then we would have them insert the names of the species for which they would like a phylogeny, which would then be separated by commas, or they can always simply upload a CSV file of the species with the respective family and genus columns populated. Lastly, we would ask them to either go with the predefined tree, which is already offered with every single taxon, or if they would like to use a custom one, they can always go ahead and do that as well. For the sake of conserving time, I have a screenshot of the input query as well as the output result. We were interested in looking at the phylogeny of a plant species, and then we inputted the names of the species of plants, and then chose the standard predefined tree, and then hit build. The output on the right side, we see 5 names of the species that we originally inputted, organized as a cladogram. We also added a function to observe the tree in the form of text instruction, aka code. Here we see a much larger tree with hundreds of species of plants, which is of course generated reading a CSV file. A file such size would typically take up to 1.5 minutes to finish building. So challenges and learning outcomes. At first, I found my summer project very confusing, since I had not taken biology in over 5 years, let alone ecology. This project was borderline completely out of my programming comfort zone. Looking back, I realized it was an opportunity to learn and grow my present skill sets, not simply learning to write new lines of code in a different language, but rather the principle of learning how to work in a collaborative setting and taking instructions in order to reach the weekly goals. While beginning to learn Shiny, I found it very obsolete to read books and watch mundane tutorials. And then I was later advised by my mentor to begin applying my new learnings from those books and tutorials and enforce myself into applying it into actual code. Even just writing pseudocode and running into problems as you go, and then finding solutions to those problems is where I did most of my learning. If it wasn't for that, I would most likely still have been stuck learning how to write Hello World in week 405. This is really where I had the chance to apply deductive reasoning and essentially learn as you go instead of learning entirely from the ground up. This lesson may sound trivial, but I think this would certainly have its carryover value into my future endeavors. Lastly, in the case of Shiny, I particularly enjoyed working with its intricacies and vast variety of its applications. I believe it's a very useful tool to deliver a realistic function, or rather a visual application of your work. Shiny allows our users to gain great data insights and render actionable data to the user. It allows all the advanced analytics of R to be made available to the developer. For me, R helped me learn how to communicate results via interactive trees and actual meaningful visuals. So this is all I have for you today. Thank you so much for listening. Questions and comments are welcome. You may address them to the email provided here. And thank you.
Okay.
Thank you very much.
Any questions?
Any question or comment?
I guess my comment will be it's a very interesting project, and I'm glad you guys were able to put it together. It's really interesting.
Thank you.
You
I
are
have a
going to
question.
yes, Les.
How did you go about learning R?
Learning all, like you're asking me or asking my mentee?
You.
Me is like, I think that's mostly during my graduate school, and I need to do, my dissertation, so that, and back to then you have tons of time. You just learn by, by doing it, just Google around. I think I probably took one short R course, but that's it. Then the other thing is just you need to dive in, and if you need to do anything, and then try to find out how to do that with the specific tool you want to learn. I think that's the best way I find to learn anything. Like reading books, that's helpful, but it's not really that efficient of using your time to learn new things. That's what I learned.
Any other question or comment? Okay. So if there are no more questions, then we can go with the next speaker, Yemaya Maxi.
So my project was tomography-driven optimization of biofuels, where I focused on using corn roots to learn more about plant root architecture and the root structures. So right here in this image, you can see corn with 3 different genotypes. There's the B73, MO17, and hybrid. It was grown both in gel in a lab and in the field. So the plants grown in the gel could be imaged repeatedly with X-ray tomography at 4-hour intervals. And you'd be able to watch the roots grow. And in the field, the plants were grown, they were grown, but then they were removed from the soil there, and the excess soil was washed away, and then they were imaged. Yes, and they were imaged, and then they were re-imaged, and you can see from the lab in the soil that there are different architectures for plants for like the same kind of plant. So I had 3 data sets of corn to work with. They were all donated from Stanford Plant Science Center. So they were put in an imaging system like this that you see over here. This is a Northstar X 5000 system. So the plants are put in this system, and then from there was 2D X-ray tomography that I had to work with. And I was responsible for creating a tomography view of those 3 root data sets that I had. So I started the data analysis using ImageJ. So we decided to go with manual segmentation because of the low image to noise contrast in the images, in the slice images like you see here. So I got started with ImageJ using their painting and interpolation tools. And right here, you can see a short clip of me using their segmentation editor, going through the slices and outlining it, and then interpolating the data so that everything in between is highlighted. So there's the interpolation function here, then thresholding, an open and close function. But as a result, this is what I got on ImageJ. You can see that there's not a lot of detail, and there is some missing information. So then that's when we decided to switch over to Aviso and use some of their tools, because I found it a little bit easier to work on Aviso than ImageJ. Go to the next slide. So getting started with Aviso, I'm going to compare it to my one of my roots that you see here. So this is a 14-day, 3-inch root. That's what it looks like. That's what my tomography is supposed to look like. But if you look at this 2D slice here, it's kind of hard to see where an actual root is. So yeah, because of the low image to noise contrast, I had to figure out how to make this more easy to work with. So I was able to meet with Ali, who is an application scientist that works for Aviso, and he was able to help us get the most out of manual segmentation, since that was the route we chose to use. We could have done more advanced machine learning techniques, but because of time, we decided to go with manual segmentation. So he recommended using the filter sandbox tool, which you can see here. It's on this image that you see, and compared to this image over here, there is a lot more clarity in this image that you see. So in this slice right here, I already have some things labeled out. There's the corn grain, and then some other roots that are branching out. But looking at this image, I can see that there are a few lateral roots. Zooming in, we'd be able to see them better. So over here, you can see these are more filters. I went through all of them and found that this delineate one worked best for the roots. And over here is a volume rendering of my 10-day 2-inch root. So there's this stem that goes into the corn grain, and the light blue roots that you can see here, there's 4 of them. Those are the prime braces. Those are the braces. And then the dark blue roots are the primary roots that are all branching off. And there are lateral roots here too. You can see one right here, but there definitely are a lot more. If you go back and look at the previous image, all of these tiny things, those are all lateral roots. Also, so this week I have been working with the University of Texas at Austin in a biology and paleontology short course where I've been learning more about data acquisition, data analysis, and visualization on ImageJ, Aviso, and Dragonfly. This short course has been helpful in helping me to learn more about machine learning tools and segmentation, and so that I could switch over from manual segmentation and hopefully save time when it comes to doing segmentation on the roots. The work that I have been doing with my plant roots this summer will show up in a larger project or a new project with collaborative virtual reality. So this can be used to identify the roots more rapidly and to communicate the findings more efficiently. The training sets for this are still under development, but there is discussion with SciGlass, which is a company that helps scientists understand their complex data. Understand their complex data and communicate their findings more efficiently with other scientists. And right here is a short clip of some 3D tomography that was done with this software. This is a fly in this image. So this company specializes in large data sets, which is helpful for plant roots because those data sets are generally pretty large. But not only can you use collaborative virtual reality with things like plant roots, but this can also show up in other fields as well, like the medical field, for example. A surgeon could scan the anatomy of their patient and figure out the best way to do a complex surgery in order to keep, in order to minimize making more damages or doing something harmful that could not go well for the patient. So that concludes my presentation. Do you guys have any questions for me?
I have a good question.
Mhm.
So you mentioned gel-grown medium and field soil when you work with the corn. What kind of gel did you use? Was that special gel?
Oh, so that was not my work. That was from a research paper.
Oh.
I didn't do any of the growing or imaging. I was given the data sets that were already done.
And you say you have you study 3 data sets. Were all grow in soil or
Yes, those were all grown in soil.
what was the plan you visualize?
It was corn.
The three were corn.
All 3 were corn.
Thank you.
Thank you.
Any other question or comment?
Yeah, this concept of a 3D, of humans having 3D spatial visualization so they can see things in 3D. One of the LSU professors had a nice publication last year showing that it can be a learned skill. This is based on eye tracking and functional MRI. Jemiah, describe how you felt like your ability to see things in 3D improved over the summer with this project.
Yeah, so first I had no idea what this was, but I am able to, I think it's a lot easier for me, especially when looking at the 2D slices. I notice it a lot more than like I notice what I'm supposed to see better than, I don't know how to word it correctly. But like I understand what I'm supposed to see rather than like I know what I need and what I don't need in my images. Did I answer your question? I don't think that I answered it correctly.
This 3D spatial visualization is kind of hard to explain. You sort of know it when you see it.
Yeah.
Thank you.
Any other comment or question? Okay, there are no more comments. Let's move to the next. Presente, Autumn.
My project for this summer, I was working on classical linear elasticity and bond-based paradynamic models with my mentor, Patrick Delhite, and he also has a partner on his research project, Serge Prudhomme, who helped us a lot this summer with my project. All right, so a quick overview. We're going to talk about what is bond-based paradynamics, a little bit of my REU goal, and some different coupling methods that we use, and some coupling data that we'll go over. So a few definitions. We have paradynamics, which is our non-local model here, a form of mechanics, which is just concerned with some discontinuities and fractures. Then we have linear elasticity, our local model, a mathematical model of how solid objects deform and become internally stressed due to different loading conditions, which we will see later. And then we have coupling approaches, which is where we couple those local and non-local models, and we pair them to combine the efficiency of the local models and the accuracy of those non-local models. And then we have modeling error, which we will see later on some plots, which is the difference between the solution to the coupling approach and the solution to the classical linear elasticity model. All right, so here is a graph which just shows linear elasticity versus a paradynamic model. So this summer we used this model where we were holding two rubber bands. We were holding them both on both ends. And a force was applied to the top where somebody pulled the rubber band. So in the linear elasticity model, this is without coupling. It goes on linearly. It would go on infinitely in that straight infinitely in that area. But in our paradynamic model, it would travel linearly similar to the linear elasticity model, but at some point, because of the force, it would fail, which we see here. It's just model that 2 is where it fails. So we want to use coupling so we can combine the method of the linear elasticity model, which is going on infinitely, and this paradynamic model, so we can get a better method. So we used lots of different coupling approaches. Oops. So my goal for the summer was to investigate the coupling of the local and non-local models to combine the benefits of both. All right, so there are 3 different types of coupling methods. We have coupling where we match the displacements between the models. We have coupling where we match the stresses, and then coupling with a variable horizon. This summer, what you'll see is just data based on coupling with matching displacements, which is what I have worked on for the entire summer. So right here we have a model which showcases our linear elasticity model, which is in the black filled in dots, and then our paradynamic model, which is in the open white dots. So what I said before, coupling where we match our displacements, right here in the overlap region where the paradynamic has overlapped into the linear elasticity area, we match our displacements. This point and this, they're both matching. These are both matching. And what I was doing, I was going in, this point does not have a matching displacement. So we would do an interpolation. I did linear interpolation. I also did quadratic interpolation. So that's what we were doing. And we were also experimenting with the nodal spacing. So right here, we have a nodal spacing of 1/8 in our linear elasticity region, and nodal spacing of 1/16 in our paradynamic region. And this is also the linear elasticity region of 1/8. We also have different diagrams where we had a nodal spacing of maybe 1/16 here. We also had a region of maybe 1/32 here. So we just did a lot of experimenting with different regions and also different methods for interpolation, whether that be linear or quadratic. So now we're about to see a few different plots. So here on the left, we have our linear interpolation, and this is with a quadratic loading condition. So in our linear interpolation, we have the blue plot, which is at 1/4 for our coupling. We have 1/8 for our coupling here at the orange. And then at the green, we have 1/16. And then this red plot is a plot where there is no coupling. It's just the, it's just the linear elasticity region, and there's no coupling, which we talked about earlier, where we will see modeling error, which is where we compare this red plot with the rest. And on this side, we have the quadratic interpolation. We see that when we do it quadratically, the error is a lot less. You see our lines are way more close to the red line. It's a lot more accurate when we do our quadratic interpolation. Okay, and here are error plots. So we see here in the linear elasticity error plot, we have an error. It's really great right here for our 1/4. And then at 1/8, our error gets smaller, which we would assume. And as we get smaller and smaller with our nodal spacing, the error also gets smaller and smaller. And then here in our quadratic interpolation, we see that the error is already a lot smaller, even when we have our nodal spacing of just 1/4. But as we get all the way to 1/16, comparing the error right here, this is 0.02, here our error 0.05. So we can compare and contrast those errors when we do a linear interpolation versus our quadratic interpolation. And we also have cubic solutions. So here is the exact same method and formula that we used earlier, but instead of having a quadratic solution, we have a cubic solution. We see the same plots here in red, which is the non-coupled plot. And then in our different colors, we have the nodal spacing again of 1/4, 1/8, and 1/16. And we can see what it looks like in our linear interpolation versus what it looks like in our quadratic interpolation. And as we predicted, the quadratic interpolation is more efficient, it works better. And then in our error for the cubic linear interpolation, we see again how the error of 1/4 is extremely great compared to our error of just 1/16, where we have smaller amount of error. Also in our quadratic interpolation, our error at 1/16 is even smaller than it is in our linear interpolation. We also did different plots for a different boundary condition. This is called the Neumann boundary condition. Originally, I said we were holding a rubber band fixed on both sides, but in our Neumann boundary condition, we have our rubber band fixed on one side, fixed only on one side, where we can see that it's only fixed at one point, on the other point it is not fixed. So that's the difference between our Neumann boundary condition and the original one, which you showed earlier, where we were fixed on both sides. So again, it's the same plots, the plots at 1/4, 1/8, and 1/16. And we can see that our error, the quadratic right here, you can't really see it. It's really hard to see the different ones because it's so close in together, which we predicted. It's a lot more efficient than our linear interpolation on this side. And then again, we have the error plots. And we can see that on our linear side, our error is a lot greater than it is when we did our quadratic interpolation. All right, and those are some of the references that I had, and that's all that I had for today. Any questions?
Yeah, I have a couple of questions. I mean, when you say the cubic, when you show the cubic plot, the displacement is the displacement. I mean, are you plotting the position of the different pieces of the rubber band, or?
No, so we're plotting the cubic plot. It's not the positions of the rubber band. The rubber band is just like it's just, we didn't actually have a rubber band. That was just the scenario that we're using. What we're plotting here is we have different forces that we use. So on a cubic solution, we had different formulas that we would input into our code, which is why it's in the cubic shape rather than the quadratic one.
But
So
you label as displacement. The vertical axis you label as displacement. Normally, displacement is the how much a piece of the material have moved from the equilibrium position. I mean, I don't know.
No,
yeah,
it's correct. It's the displacement.
So this is a rubber band that is in that shape, in a cubic shape, or?
Yeah, you have a rubber band which is in a straight line, and then you apply the force, and then you get this cubic shape because you're pulling, that the force results in this cubic shape.
Okay, so you are pulling from 2 points in opposite directions. Okay.
Yeah.
Okay. Yeah, and my second question, when you compare the linear interpolation with the quadratic interpolation, the errors of those two methods, it looked that the error in the quadratic is around half of the error in the linear. For more, I mean, yes, it looked like that in most of your plot. So if that's the case, I mean, are you gaining, I mean, how, because to do the quadratic interpolation will cost you more operations. So could you, I mean, are you getting the same result that just using a finite mesh, but with the linear interpolation? Could you reduce the error by half just in that way? You know, be equally efficient? I don't know if you have thought about that.
I'm not sure if I understand your question, but if you're asking the methods that we used, could we just use the linear interpolation and get the same data as when we use the quadratic interpolation?
Yeah, the quadratic error, it looked like it's half of the other error, not for most of your plot. But to do the quadratic interpolation is costing you more operations. The computer have to do more operations. So if you use that additional computing time for doing a finer mesh and using the linear interpolation, I mean, you know, eventually you want to find out what is more efficient, the quadratic, you know, or the linear, you know. So I'm just curious if you have thought about doing that experiment.
No, I personally have not, but I still will be working on this project. So that's something that we could take into consideration going in the future.
Okay, thank you. Okay, there are no more questions. We can move to the next person. Thank you, Anson.
Thank you.
Sarah, are you ready for? And you are on mute, so we will hear you right away.
Hello, everyone. My name is Saida, and this is my REU presentation of summer 2021. Today, I'm going to be talking to you about computational fluid dynamics. My mentor throughout this experience is Dr. Kumar, who is a chemical engineer professor at LSU. So my project is a combination of computer science and chemical engineering. And for those of you that might not be as familiar with the term, chemical engineers are the ones that apply the principles of chemistry, biology, physics, and math to solve problems that involve the use of fuel, drugs, food, and many other products. So the goal of this project is to innovate the field of chemical engineering using the help of computation. If we could then computationally modularize aspects of this field, we will then be able to save time, money, and reduce pollution. My contribution to innovate the chemical engineering field is shown throughout my work this summer, as the work I have done this summer helps in developing better closure models for drag forces versus relative velocity. And this type of studies help in improving the forces versus velocity relationship in fluidized beds, for example. But in fluidized beds, there are billions of particles. And unfortunately, this level of detailed simulation is not possible as of today. So we do something called averaging of equations instead. And this is exactly where the periodic ellipse problem comes into play. So for this problem, this was given to me by my wonderful mentor. I have 3 different geometric figures. Each figure has a different number of particles. Each particle is set in a specific location, but they're free to rotate. And my goal for this was to change the kinematic viscosity so that I could simulate different Reynolds numbers. I was able to put together 27 cases throughout the summer, but out of the 27, I'll be showing with you guys 6 of those. So over here we have case 1. This red over here represents the particle and the blue represents the fluid. And as you guys can remember from the previous slide, the Reynolds number is just h times u over v, where h is the height between the plates, u is the plate velocity, and v is the kinematic viscosity. So to understand what Reynolds number even is, let's take, for example, honey and oil. Honey and oil have a very high kinematic viscosity number, which translates into a low Reynolds number, where water has a very low kinematic viscosity value, which translates into a high Reynolds number. When taking a look to the figures over here, these are the graphs that I obtained from the simulation. They're the time series of this simulation. The very first one represents the angle of inclination of the ellipse. The second one represents the angular velocity. And the last one represents the torque on the particle causing the rotation. And all these graphs show a very regularly periodic response to the uniform force and velocity of u equals 1. I do want you guys to notice that these particles are perfectly in sync throughout the entire process. So upon increasing the Reynolds number to 100, still focusing on the 2 ellipses interaction, we see a relaxation response. So for instance, when the ellipses are oriented horizontally, the angular velocity is very small, and it takes a long time for it to move. But once it starts moving, it reaches the vertical position very quickly and returns to the horizontal position. And once again, here our ellipses are in perfect sync, but we see that relaxation behavior. Moving on to the next case, here we have 4 particles and the Reynolds number is equals to 5. I do want you guys to notice that the particle on the upper left and the particle on the bottom right are perfectly in sync, whereas these 2 particles are in sync as well. And we're gonna move on to the next simulation. And once again, we're gonna see the same behavior and synchronization as to particles wise, but we do reach that relaxation behavior one more time. And what's interesting about this one specifically is that when we take a look at the angular velocity graphs, we see a phase difference. So these are laid out just the way that the simulation were laid out. So here we have particle 0, particle 1, 2, and 3. And as I mentioned to you guys before, particle 0 and particle 3 were perfectly in sync. And as you guys can tell, these graphs are identical. And I also told you that particle 1 and particle 2 were in sync. And as you guys can see, these graphs are also perfectly identical. Moving on to the very last case, here Reynolds number is equals to 5. I have 6 particles. I was not able to find a pattern in between them, but this was integrated from 0 seconds to 400 seconds. So maybe the student that comes after me next summer will be able to integrate it for longer and see if they can find a pattern. However, if there is not a pattern, it doesn't really mean much. It just means that this is actually better for mixing the previous simulations we had before. So it's not like a bad thing. Some of you might be wondering, like, why are the particles moving? Well, the forces acting on the particles are unbalanced. And if the net force is not 0, the particle will move. You guys might also be wondering, what are the forces that are acting upon these particles? And well, we have the shear force by the fluid on the particle surface, we have gravity, and we have buoyancy on the entire volume. Moving on to the same case, but when the Reynolds number is equal to 100. Once again, I did not find a pattern between this, but we do see that relaxation behavior that seems to be very like a pattern. Whenever we increase the Reynolds number, we seem to be finding the relaxation behavior. And so something very important that we found throughout these experiments was the more particles you introduce into the mesh, the more chaotic behavior we seem to be finding. While when we have fewer particles, they seem to be reaching synchronization very quickly. So throughout this experience, I was able to learn a whole lot of things. Some of those things were OpenFOAM and ParaView, which are open source software. With OpenFOAM, I put together my meshes. I put where the particles were going to go. I gave them the motion they were going to have. With ParaView, I was able to visualize everything. And I was also able to put together those simulations that you guys saw. But overall, my biggest takeaway was chemical engineering. I had no idea what chemical engineering was before coming into this. And I feel like I learned a great deal. And for that, I would like to thank my mentor. So thank you. With that, are there any questions?
I have a quick question. You mentioned you didn't really find clear pattern, but did you find any subtle, any pattern, the particle simulation?
Yeah, so for the first case where I had the two particles, I saw a clear pattern there. For the one that I had the four particles, I also saw a clear pattern. So there seemed to be that on the first case, the two particles were perfectly synchronized. And in the second case, I was able to see that two particles were synchronized where other two particles were synchronized. But with the very last case, there was not such synchronization between the particles whatsoever. So it was a very chaotic behavior.
Thank you.
Yeah.
Any other question or comment?
Just a comment. You did a fantastic job. I'm really impressed with what you did.
Thank you, Dr. Kumar.
Yeah, I have just a question. I'm curious. I mean, the problem you are solving is symmetric, with respect to the line in the middle.
Correct.
No,
Yeah.
So,
Yeah.
so that symmetry should be reflected in the behavior of the particles, and you find it for a small when you have 2 or 4. So, as you say, if you run it for longer, will you find that behavior? I mean, it's a numerical method or not?
Sarah, do you want to answer that? That's a very difficult and a very profound question. And I think the answer to that lies in stabilities of these flows. So you may have a symmetric solution, but if it is unstable, then it goes into symmetry breaking bifurcation, and you will have multiple solutions, etc. And so there's a highly nonlinear behavior that we are fundamentally interested in. The reason I jumped in is we haven't discussed this specific answer, but that's one of the driving forces for us to look at when these symmetries are broken, how they are broken, and because when you have millions of particles, there is no symmetry, right? So what can we learn in the symmetry breaking process to learn about cluster formation? Why do the particles form clumps in fluidized bed in real life? So it's inspired by that. I didn't mean to inject, Sarah. If you have a comment to make, please go ahead.
No, okay. Thank you, Dr. Kumar. I appreciate that.
Aaron, are you ready?
Yes. Okay, yeah, so this is my project on quantifying performance of quantum teleportation with an arbitrary resource state. And this was done with Dr. Mark Wilde and his graduate student, Vishal Singh. So this has a lot to do with quantum information theory and a lot of information theoretic concepts. So I'll just fix some definitions. So in classical computing, like kind of what we're doing now, the way we're able to communicate, and really the birth of modern technology and stuff like that is based around bits and binary digits, zeros and ones. And there's interesting theorems from Church and Turing, Shannon, about the types of computations and things you can calculate using and or not gates. So these are called universal gates. of classical computation. And it's kind of taken for granted sometimes that in a lot of these processes that are going on in the computer or being communicated around on networks and things like that, this classical information, and that's kind of a common term, like for just a binary digit, is classical information. It can be copied, stored, moved, and it can be copied. You can keep a copy and then send it to someone else, and that's very important. Yeah, so now in this new quantum computing, quantum information kind of field, we'll be dealing with quantum bits, which are qubits, and they can perform universal computations, universal logic using 2-qubit logic gates. They're called C0, controlled not, and the Hadamard operators. And these qubits, and this is a little bit of mathematics down here, these qubits can exist in superpositions of 2 independent states. So if you have a 0 and a 1 state, just like in classical computation, these are 2 distinguishable states, but they can exist as a superposition of these 2 states at the same time, you know, kind of say. But in reality, these are complex. They can take on complex values, these parameters. So they have 2 independent degrees of freedom. And when you start adding more qubits together, the total number of available states increases like 2 to the n instead of linearly, as in Moore's law. So this has been a very interesting field of research in the past few decades. And this is Google's CEO with their quantum computer. It works on this kind of C0 Hadamard architecture. And one of the hallmarks of quantum computing and all this kind of quantum information is that qubits cannot be copied. There's a no cloning theorem. So at any point that you want to communicate or pass information around, you can't just you know, copy paste it to someone else or send it in the same kind of file. So it requires one more resource. So that's where this quantum entanglement comes in. And there's a lot you can say about entanglement, but well, I'll just call it entangled. And really, there's entangled qubits. So we'll call them E-bits. And these E-bits can be generated by using our 2 universal gates, which are the Hadamard and the C0 operation here. And by passing two qubits that are in an initial state to these 2 operations, you can create this entangled state where these 2 qubits are now in a pair, and they have this strong correlation that is very fragile from interference from the environment, but also very resourceful and very useful for interesting quantum protocols and quantum information things. So and you can do some things with that in classical computation, but I'd like to consider what you can do with this with networking. So if you want to think of like a quantum internet. So in the analogy to a classical sense, in classical networking, if I have 2 parties here, Alice and Bob, and they're connected over, and here I'll just show like a LAN cable. Now, if Alice has some information on her computer, which is stored somewhere in like RAM or ROM or something, and then she can encode this information, essentially copying it, and it gets encoded onto, you know, pulses. If she actually measures the voltage values on that wire, they'll be encoded into there, and then this information will get passed to Bob. But they both retain the same information. Now, in the quantum teleportation, quantum networking case, it takes a little bit more. So initially, if Alice and Bob share one part of this entangled state, so Alice has one part of an E-bit, and then Bob has another part of an E-bit, and Alice has this qubit down here in the lower left that she would like to teleport, then she can use her quantum computer and the classical computer to make a measurement with her classical computer or with her quantum computer, and then make a classical communication to Bob, which he can then use to reconstruct her qubit at the destination. So you use it, and then you've expended an EBIT and you've used classical communication to reconstruct this qubit. So it's very, very, how do you say, unexpected, very interesting. And this is how you'd have to do any kind of communication on a classical computer. So if you had like a quantum memory, which is pretty hard to do, then you'd have to teleport a bit from the memory into processing. Or if I wanted to send the qubit out anywhere, like out to space, and they've done this in experiments, then you have to use this kind of teleportation to do noiseless communication. And this is the same thing. And this is called like a protocol. So if Alice and Bob if Alice would like to teleport this state psi a prime to Bob, then they can share this maximally entangled state. Alice can make a measurement, perform classical communication to Bob, and then conditional on that communication, Bob can reconstruct her state. And and then this has been shown since 1993. Yeah, very interesting stuff. So what we've been, and then this has advantages for increasing, because you can actually do this process backwards and increase your channel capacity. That's one application. If you want to do distributed quantum computing, this is something that you'd have to do for like quantum internet. But in the near term, a lot of things people are interested in is its enhancement towards cybersecurity. So there's a quantum analog to something like public key distribution and RSA. That's called quantum key distribution. And this is an active field of research that will come along at some point fairly soon. And so in our work, we would like to investigate, and we have been investigating, what and how this system or this kind of protocol would work when our EBITs are imperfect. So if there's noise in the system, then we need to correct that, or we need to know what the absolute minimum that we can operate under. And this is a lot of information theory that is already being done in like a classical sense. And so we construct semi-definite programs that can run optimizations to find the optimal solution and the optimal error threshold. And and this would have some kind of application to quantum error correction and a lot of other kinds of information processing techniques that are necessary to realize this quantum computing future. Yeah. So if anyone has any questions, I'd love to take them.
Yeah, I have a question. So this semi-definite program is a minimization approach?
Yes. So if you're familiar with something like in machine learning, almost how you'll have an objective function, and then you'll have a set of constraints on that objective function, and then you'll want to minimize the objective relative to some set constraints, and that's the same thing that we'll be doing here. But in the semi-definite case, it's called semi-definite because these are matrices and they're not always linear functions.
Okay, and you minimize that not using machine learning. I mean, you minimize that problem using an algorithm.
Yes, numerical solver. Yeah.
Mm-hmm. Okay.
So Theron, go back to the plot that you had of the figure of teleportation.
Here.
So, so Juana, what we're assuming here is that this state here is no longer perfect, and it's subject to noise. And then we want to allow for a minimization over all possible protocols of this form. Those protocols are called one-way local operations and classical communication. It turns out that that class of operations is hard to optimize over in a mathematical sense. And so what we do is we relax the set of operations to include like a larger set that can be characterized with semi-definite constraints. And then when we do so, we can write the error between the ideal. So teleportation realizes an ideal qubit channel from Alice to Bob. So then when we allow for this enlarged class, we can write the error between the ideal case and the actual case as a semi-definite program. The project is similar conceptually to what Eliza Siddiqui and I ended up doing, but we're using a conceptually different way to enlarge this class of operations.
Okay. Okay, thank you.
So, and thank you, Theron, for coming here this summer. It's been an enjoyable experience for me. It's been nice to have you on board, and I look forward to writing a nice research paper with you and Michelle.
Thank you. I've also enjoyed it.
Yeah.
Amaya is the last speaker. So wherever you are ready.
Okay. Good morning. My name is Amaya Holmes, and I am a sophomore at Savannah State University majoring in computer science. And for my research project, me and my mentor investigated to see if wells in northern Louisiana held grounds for any geothermal potential in those wells. Before we dive into everything, let me provide some background knowledge on some key things. Geothermal energy is basically heat that comes from within the earth. Water and or steam carry the geothermal energy to the Earth's surface. From there, the energy can be harnessed to generate clean electricity. However, for this to happen, a region with high or medium temperatures resources is needed. So how these plants work is fairly straightforward and simple. So hot water is pumped from deep underground through a well under high pressure. Eventually, when the water reaches the surface, the pressure drops, and as a result causes the water to turn into steam. Then the same steam turns a turbine, which is connected to a generator that produces electricity. The steam then cools off in a cooling tower, condenses back to water, and the cool water is pumped back into the earth for the process to happen again. There are few geothermal plants within the US, and with these few, they reside exclusively on the western side of the country. This is primarily due to the fact that the most active geothermal resources are usually found along major tectonic plate boundaries, and one of the most active geothermal areas encircles the Pacific Ocean, which is the Ring of Fire. However, we have seen that there are large spots that hold geothermal potential in eastern part of Texas, along with the northern portion of Louisiana. So, what makes geothermal so special, and why would Louisiana benefit from it? Geothermal energy is clean and sustainable energy. These plants impact the environment very little, and this energy can be extracted without burning any fossil fuel. It's also a constant source of energy that just keeps on going. While energy such as wind and solar are also clean, they depend on certain factors, like, for example, how solar energy needs the sun to be shining and wind energy needs wind to be blowing. The only way for geothermal energy to stop producing or to be depleted would basically be for the Earth to be destroyed by the sun, which hopefully won't happen for another billion years or so. Also, they require very little land. They use about 1 to 8 acres per megawatt, while something like a nuclear plant ranges from 5 to 10 acres per megawatt. It's beneficial to the local economy and also provides employment opportunities. This is a $1.5 billion per year industry, and has directly and indirectly provided between 12 to 27,000 jobs. Lastly, this energy source is safe from surface influences. Louisiana is in a region that experiences a lot of hurricanes. So since geothermal energy comes from the ground, this energy source can't be wiped out by a hurricane and other elements of that sort. When looking at this map, we can see that there is a large spot in Louisiana, which is a very promising location. So for this project, we investigated if it was possible for northern Louisiana to set up a geothermal power plant in certain areas, essentially meaning do some of these wells meet ideal conditions. Over the last two months, I spent learning about geothermal energy and the processes of how these plants work. I had no prior knowledge to Python, and I spent time learning that along with refreshing my knowledge on stats, which allowed me to make my graphs and interpret what a lot of this data was saying and why was it important. There isn't an endless supply of research available on this specific area, but there is some. Thankfully, we were able to find a lot of raw data thanks to a thesis that was published from LSU's Department of Geology and Geophysics by a graduate student named Tessa Hermes. From there, we looked at two different parishes in Louisiana, Morehouse and Union. We looked at data from 37 different wells within the Morehouse and 23 wells in the Union. When looking at this data, we were looking at temperatures above a certain threshold along with the highest geothermal granite. Geothermal granite is the amount that the Earth's temperature increases with depth. Ideally, we want these levels to be high. We want there to be a high granite level at a low depth. We then put all this data into data sets, and from there we filtered out wells that had fairly high granite levels and reflected those into graphs. Let's look at the Morehouse. Again, we looked at 37 different wells in this area with a minimum temperature being 101.22 degrees Fahrenheit and having a max temperature being 257.0 degrees Fahrenheit, along with them having a max depth of 9,521 feet, while the lowest reaching only 513 feet. These depths and temperatures are how far down was drilled and the temperature at said depth. Of these 37 wells, 10 had a geothermal granite higher than 29 degrees Celsius per kilometer. The lowest depth of these we saw was 1,452 feet with a temperature of 110.26 degrees, which had an incredibly high granite level. These in this graph right here, you can see that these dots are bigger than, these dots. These bigger dots are signs of geothermal anomaly, which is something we want. We want to drill at these spots right here. Lastly, let's look at the Union. For the Union, we did only look at 23 wells, which from here, which is a bit less than the Morehouse. From the data, we saw that there was a minimum tip of 101.39 degrees Fahrenheit and a max reaching 322.54 degrees. A major difference between these two was how much deeper the Union went. There was one well that drilled up to 13,655 feet. And from these wells, only 7 had a granite level that was higher than 26 degrees Celsius per kilometer. And again, we're seeing these big dots, which are the geothermal anomalies that we want. There are individual wells that are producing promising results from a bunch that we saw. The 23 wells from Morehouse and the 7 from the Union would be the most ideal. These wells will be an ideal location for a plant on a smaller scale. While they aren't reaching high temperatures like places in California, since Cali is along the tectonic plate, it is reaching temperatures that are still favorable. They would be great for communities by providing majority of electricity and providing economic benefits. This will cause there to be a less of a need and use of unclean energy. And I have my resources, and I do want to say thank you to everyone, especially my mentor and also Dr. Moreno for giving me this amazing and beneficial opportunity.
You are very welcome. Questions, comments?
So you mentioned 2 different parishes in Louisiana.
Yes.
Have you thought, is there any reason why you chose there and other potential parishes or states?
So when we were looking for or trying to focus on a region, there really wasn't much data on any other region besides just these 2. So that's what we decided to pick because it provided the most data for us.
And do you have something in mind in the future, other states or other parishes?
Oh, yes, of course. So I'm definitely invested in this project now because I really had no prior knowledge to any of this. I had no clue about any of this. So I definitely am invested in finding other areas that might not have any plants and just researching if it's possible for there to be future ones.
Thank you.
I have a couple of questions. I mean, the size of the dot, how do you determine that?
So the dot size was based on how high the linear granite was. So the bigger the dot, the higher the linear granite was for those.
Yeah, and how do you get the that linear graph? How do you, I mean, this is a measurement from the data set you got? Or?
I'm sorry, repeat the question.
Yes, how do you get that linear graph?
Oh, it's the so it was provided for us in the thesis. The linear graph was also provided, so I just reflected those into the graph, into a graph.
Okay. Yeah, and my second question, why this is happening in Texas and North Louisiana? If there is no tectonic plate, why the...
Okay, so I picked Louisiana mainly because since the program is in at LSU, I figured it would be more of a ideal place to put it rather than looking at Texas.
Yeah, but why is hotter? Why the soil, the land is hotter here?
Oh, I actually didn't look into that. I'm sorry, I didn't gather any information on that specifically, but I can only assume that it's from, well, I don't want to say anything wrong, that's why. So
we don't know, so we don't realize.
I don't want to say anything that's wrong, but I'm not too sure why exactly, but I can look into that in the future.
Okay, thank you.
Mm-hmm.
Any other question or comment? Okay, great. So we are a little late. So let's take 10-minute break until 11. Okay. And then we will come back with the presentation. Altan will be the first one. Okay.